given a model of the beam which is under undeformed situation, it has been curved. For example, this beam maybe pre-made just like this. Okay. And for simplicity, in this section we talk about is the curved beam is imperfect in the circular segment. So that means for each kind of part of the fiber curve, they share the same center of the curvature. So that is the assumption. And before we dig into the detailed technical calculations, I can tell you the influence of the pre-made curvature on the beam basically is on the influence is onto shifting the location of the neutral axis. That's it. So one period. So just one word. That one. Okay. So for this one, because due to the curvature of the pre-made the beams, then the one key step in the calculation will be how to calculate the neutral axis, and the same concept but a little bit different calculation step. So with the handout, and in this one I don't need to draw the figures, and this one, assuming this one is undeformed, and before deformed, this curvature has been defined by theta. So basically theta is one of the dimensions given by the progress. And here again we still take up the same convention. That means we attach the origin of the coordinate systems onto the neutral surface. Okay, so that means indicating, if you like, you can say DE is the neutral surface. Doesn't have to be at the middle, or depends on the cross section. It could be upper or could be lower, depends on the cross section. So if you like, you can mark the DE is the neutral surface. And once this beam is being deformed and under the pure bending, so the pure bending will curve more, and the contribution due to the curving of the bending is by delta theta. Due to the application of the bending, that will contribute additional delta theta to here. So the amount of the delta theta representing is the response of the material to loading. Okay, so right now the remaining is how could we relate this response deformation to loading. So that is the one I can show you quickly here. The formulation starting from by identifying by the location of the neutral surface. And from the undeformed, we say that the distance, the radius of the neutral surface position is r. And so that means the fiber D, which is on the neutral surface, and before deformed is equal to r times theta. Then after deformed, so that is before M applied. Then after M applied, then the D becomes to D prime, and that is again on the neutral surface, and the length equal to, by looking at here, and due to deformations, then the curvature change. So that means the radius of the curvature change as well. So the location of the neutral surface and the radius of the curvature become r prime. We don't know that value, but here we just take out using the symbols. R prime times theta plus delta theta. And because this is on the neutral surface, they must be equal to each other. Okay. the two terms must be equal to each other. So that means here we have is r theta equal to r prime theta plus theta theta. So we call it, let me call this equation 1. So with this information, this is the first step, and then the second step is we calculate the deformation. Simply follow up our reasoning in this chapter. We calculate the deformation, because from the deformation, then we can calculate the strain, and by calculating strain, we can calculate the bending stress. So that is our strategy. Okay. So we calculate deformation. Deformation is this. Because the neutral surface is undeformed and there's no deformation on the neutral surface. So to calculate deformation, we can pick up any fibers. For example, we pick this fiber, and that fiber is locating, let's say, has a coordinate y. Okay. So here the deformation will depends on, from here you should have a feeling the deformation depends on their location away from the fibers, from the neutral surface. Basically, that is a distance away from the neutral surface, the same concept. So the deformations, and for example, on the fiber, for example, fiber JK, and which is the will be equal to delta, and by definition we take the deformed after deformed minus before deformed. So JK prime, that is this one. So this one is r prime times the theta, r prime times theta prime minus r theta. This is deformed minus original. So we simply plug in the information, and what is r prime? We try to plug in. Again, y is to denote the location of the fibers. So here we can, using the geometry, here the r prime equal to r prime minus y, and times theta prime minus r theta. And again, r is r minus y. Okay. So we get this one expanded, so that is r theta prime plus y theta prime plus minus r theta plus y theta.
Will you substitute theta prime for the theta plus delta theta, or no? I don't know.
Yeah, so here I substitute is this term to this one.
Yeah.
And then again this term to this one. Okay, so here, here, let me rewrite this one. This is basically r prime theta prime. Okay. So from here we can see cancel this term and this term. So the deformation is minus y times theta prime basically this is y theta minus theta prime. Okay, and let me rearrange. So basically that is minus y times theta theta.
Why did you cancel r prime theta prime now?
Because using this equation.
Oh, okay.
Yeah. Okay. So therefore we have the deformation. So therefore the strain. The normal strain epsilon x. And again, in our corner systems, this is x-axis. X-axis is pointing to the axial direction. So this one, by definition, is delta deformation. The strain, by definition, is the deformation divided by original length.